Welcome to our webinar. I would like to start by introducing myself. My name is Petra Meyerhoff and I work as a biologist at the Walz company. Today I will talk about the MINI-PAM-II porometer, a special leaf clip for the MINI-PAM-II. The combination of Porometer and MINI-PAM-II gives this leaf clip much more features than other porometers have. Or you can say, it's more than just a porometer. The webinar will be divided into the following topics: the instrument, where I will introduce the porometer itself, leaf angle and sun incidence, some information about leaf angle calculation and solar incidence determination, the pneumatic schema, this gives you an overview of how the porometer works. Then we will move on to the individual measurements and measurements with the help of stability control, and I will show you how the porometer measurement can be used in combination with MINI-PAM protocols. And here I will show you some application examples. And at the very end, I will mention some useful accessories. With the porometer, we now have an instrument that perfectly complements our popular MINI-PAM. It supplements the chlorophyll fluorescence analysis with information about stomatal control. Of course, giving the stomatal conductance, but also other parameters like evaporation rate and VPD are calculated. This gives you multifaceted information about your samples, which can be either leaves or needles or something else. You can do short individual measurements or longer experiments. You can use the porometer right away. The porometer is as good as maintenance-free. Only a short adjustment, which is called match, of the humidity sensors and a single-point calibration of the external CO2 sensor is recommended. But these can be done without any additional tools. Our company attaches great importance to good quality and long-lasting devices. Some of our first devices from 1972 are still in daily use. So that's why this porometer is also compatible with all MINI-PAM devices which have been sold so far. After a short firmware update, which is free of charge and comes with the software, you can connect the porometer to your MINI-PAM-II. So let's have a closer look at the porometer. Here you can see the porometer. On the left is the leaf chamber which encloses the sample. Let's zoom in. This is the external PAR sensor, which can be used to measure ambient PAR or to calibrate the PAR list. At the bottom of the chamber is the touchless infrared temperature sensor for leaf temperature determination. The sample area is 1 cm in diameter and can be used for many different samples. Here you can see a clipped leaf and a needle. Later you will see also a clipped calanthe leaf. There are so many different samples with very different measurement requirements. There are thin leaves, thick leaves, firm leaves, fragile leaves. That's why we decided to make the closing mechanism of the porometer adjustable. You already know the type of closing mechanism from the standard leaf clip of the MINI-PAM-II. The porometer now features a slider that changes the spring working length and compression, and thus the closing force of the chamber. These mounts here are for the MINI-PAM-II fiber and hold it in the correct position, as you can see it here. Via the fiber, the MINI-PAM-II now performs the PAM measurement, which I'm sure you are familiar with. You also know that if you want to determine quenching parameters, for example, you must first determine the maximum quantum yield. To do this, the sample is required to be dark adapted. This can be very difficult when you are in the field under a sunny sky. That's why we offer a dark shield that allows you to easily shield your entire sample area from ambient light. The only light which your sample receives now is the measuring light, saturation pulses, and its fiber. To trigger a measurement, you can either use the buttons on the MINI-PAM-II or you can use the trigger buttons on the porometer. In this case, the red button triggers the storage of the porometer data and the execution of the saturation pulse. If you want to have porometer data without your leaf receiving a light pulse, for example during the dark adaptation phase, you can simply press the black button and store only porometer data without executing a saturation pulse. This leads me to the question, what is the porometer data? There are humidity, temperature, pressure sensors to determine the exact water content at various positions in the gas path of the porometer. You already know about the touchless infrared temperature sensor for leaf temperature determination and the PAR sensor. And of course, there are flow sensors to control the pump and the airflow and to indicate when the system is closed. But the Porometer also has an ambient CO2 sensor to provide information about the CO2 concentration in the environment, which can vary considerably, for example in a greenhouse, as you will see later in this presentation. And the Porometer has GPS, time, a gyroscope, an accelerometer and a magnetometer for the determination of sample position, sun position, leaf angle and the possible sun inclination on the leaf. The effect of leaf angle on light interception efficiency, photosynthetic rate and yield has been investigated since the 1960s. Thanks to the evolving sensor technique, it is now much easier and there's still a lot to be done. With the GPS and time, the MINI-PAM-II calculates the position of the sun in relation to the horizon. Using the magnetometer, gyroscope and accelerometer, you can obtain the Euler angles of roll, pitch and heading, which determine the position of the leaf relative to the north-south axis. Combining these two information, you can calculate the angle of incidence. This means the angle at which the sun radiation hits the leaf, or given an incident in percent, the reduction of sun radiation by the leaf orientation, compared to the position where the leaf is directly orientated towards the sun. The orientation toward the sun would be 100%. In the MINI-PAM-II, this information looks like this. This is a screenshot of the MINI-PAM-II data memory, showing dataset number 76. With the flip button in the upper right corner, you can scroll through the data, switching from saturation pulse data to Porometer data or the GPS and positioning data, as you can see here. In the first line is the data number. In the second one is the GPS information, here showing the garden of our Walz headquarters. The next lines are raw data, giving information about the signal quality, for example the numbers of satellites and the Euler angles. Then the calculated parameters of leaf and sun azimuth and slope. And in the bottom the angle of incidence. And that this leaf in this leaf orientation was only possible to get 17% of the sun inclination, which would have been possible facing the sun directly. Let's come back to the Porometer information. Next, I want to show you the pneumatic schema. The ambient air enters the Porometer and first passes an air-in buffer. This buffer is not a requirement, but buffers for humidity peak fluctuations. Then for system safety, the incoming air is filtered through a sterile filter. It passes a pump, delivering the air at the present flow rate. This is controlled by the subsequent mass flow meter. The air is now analyzed in the reference analytic cell to determine the water vapor concentration within the ambient air. Then this air passes the leaf in the leaf chamber and absorbs the humidity released by the leaf. In the leaf chamber, additionally, the leaf temperature is determined and the PS2 fluorescence can be analyzed by pump technique. The air enriched with humidity evaporated from the sample is then analyzed in a second analytical cell, the sample analytics. The differences in water vapor concentration of incoming air and sample enriched air is the basis for the Porometer parameter calculation. With the second mass flow meter, the system provides information about the amount of air coming from the leaf chamber and thus about the system's airtightness. Finally, the air is released through the exhaust. The Porometer application is dynamically integrated in the MINI-PAM-II software. When you start the MINI-PAM-II without a Porometer, you will have the familiar order of the main application windows. First basic, then primary data, followed by quenching analysis. When you now connect the Porometer application window will be in between primary data and quenching analysis. With this Porometer window, you can access almost all Porometer-relevant functions. In the center of the screen is the graph with some numerical values. If you want to see more values, you can simply tap on the screen and you will get to the values view. By tapping again, you will return to the normal view. On the right-hand side, you see the SAT button, which triggers a saturation pulse measurement. When a porometer is connected, every time a saturation pulse is executed, the MINI-PAM-II will also store all porometer data. Here in the bottom is another helpful button. It's a shortcut to the settings menu of the porometer. Here you can perform the match or alter porometer settings like changing the pump flow. By the way, we provide the widest flow range for porometers on the market. You can measure with 40 micromoles per second up to 200 micromoles per second, which is good for highly evaporating leaves. I often differentiate between single measurements and longer experiments. With single measurement, I mean the fast acquisition of stomatal conductance, which takes a couple of seconds. You just clip a sample and trigger a measurement. You use the red button on the porometer or the SAT on the MINI-PAM, or without a saturation pulse, only the porometer data with the black button or save. For your convenience, the porometer features an automatic stability detection. You can activate this feature in the porometer settings and it automatically evaluates the conductance data. Here, for example, it is defined as stable when the changes in total conductance are less than 0.3 millimoles per square meter in second in a 2-second interval. Here's a demonstration of such a measurement. I clip the leaf and you can see the change in flow at the moment when I open and close the leaf chamber. Then I push the saturation pulse button. The MINI-PAM-II now evaluates the conductance and beeps as long as it isn't stable. As soon as the conductance values meet the stability criteria, the MINI-PAM-II stores the porometer dataset and executes the saturation pulse measurement. When the measurement is done, the beeping stops and the SAT pulse button turns off again. The porometer gives reliable data. Here you can see repetitions of single measurements on 3 different rubus leaves. Leaf 1, here in red, was a healthy mature leaf showing the highest stomatal conductance level. An older mature leaf showed less stomatal conductance with a little more than 100 millimoles per square meter in second. The lowest stomatal conductance value was observed in leaf 2, a young leaf. The measurements were done at similar spots on the leaves. Often one porometer evaluation criteria is time. How long does one measurement take? A measurement of porometer data is 1 second. Combined with a saturation pulse, it is 2 seconds. The time of fast acquisition of stomatal conductance is sample-specific and takes about 15 to 30 seconds. The time depends on the sample and the applied flow speed. Here is some data showing measurements of stomatal conductance on various leaves. These measurements were done at the standard flow rate of 100 micromoles per second. In this experiment here, you can see that each sample took about half a minute or less to stabilize. The porometer data was recorded continuously each second. The grid resembles a minute. The red circles indicate manually executed saturation pulses, most times when the sample has been stable for already quite some time. But with the MINI-PAM-II, you can do much more than just a yield measurement. Some standard experiments, for example, are light curves or induction curves. And of course, you can use the porometer also in those or other procedures. As I already said, whenever you execute a SAT pulse, the porometer data will be recorded as well. If you apply the stability criteria, only the first measurement will be evaluated for stability, as you expect stomatal movement during the experiment. Here you can see an induction curve made with a Taraxacum leaf. The new WinControl 3 version, which is now available on our homepage, features a better color code for the porometer data. But here you can see the stomatal opening during the induction curve. Even though it stabilizes at the end, it is not the maximum stomatal conductance the Taraxacum leaf can have. When I increase the actinic illumination, the stomates even open up wider. In this experiment, every data point provides chlorophyll fluorescence and porometer information. For some experiments, you may want to have some more porometer data in between the saturation pulses. This is of course easy to program with the WinControl 3 batch file, But to make this option also available in standalone operation, we lately introduced the new clock function, which is now available for all when you download the new Win Control software and execute the firmware update. In the main menu, in Program and Clock, is the clock setting SAT plus numbers of Poro only. Here you can define the settings of this new clock item. You can set how many Porometer measurements will be stored in between the data sets of Porometer measurements combined with saturation pulse analysis. Now you can choose this program routine as clock item. It is an ideal tool for short or long monitoring experiments, and I used it in the following experiment. In this experiment, I monitored the tomato leaf for 6 days in the small Walz greenhouse. The weather was quite unsettled over these days, alternating between sunshine and clouds. Here you can see the natural light fluctuations and the corresponding changes in the electron transport rate. Also, the stomatal conductance varies during the day. And in accordance with the literature, this tomato leaf does not fully close during the night. This experiment shows why it is good to have some information about the ambient CO2 level. You can see, indicated in gray, that there are significant changes in the ambient CO2 levels in the greenhouse during the day. I want to show you another great long-term experiment. Here I measured a calanthui leaf which was grown under a 12-hour day and night cycle with 680 micromoles per square meter in second. This is a picture of the porometer during the experiment. Naturally, the stomatal conductance of a calanthui leaf is rather low. Here you can see the outstanding sensitivity of the porometer. I started with a well-watered plant. Each day, the stomates are closed at the beginning of the light phase. As soon as the ETR rate drops down, probably due to the lack of CO2, the well-watered calanthui opens up the stomates. Every day a little less. Here you can see day 1, here you can see day 2, and here you can see day 3. During the night, the stomates open up to fix more CO2. The highest stomatal conductance value which was observed was about 38 millimole per square meter in seconds. This really shows the sensitivity of this new porometer leaf clip. Fast acquisition of stomatal conductance, combined with yield measurements, combined with classical PAM experiments, or even monitoring. The MINI-PAM-II with Porometer leaf clip is a great tool for your research. Here at the end, I would like to draw your attention to some more accessories of the MINI-PAM-II which go well with the Porometer. For example, the spectrometer, of course the barcode scanner, and the one I personally like very much, the great 2054L external LED light source. It features red, green, blue and white LEDs which can be controlled individually, so you can freely adapt your actinic light conditions. This was today's information about the MINI-PAM-II Porometer. If you have questions, you are very welcome to contact me. Thank you for your attention.